Many software developers spend their days tracking the release of new foundation models. They study benchmark matrices, argue over context window lengths, and debate the merits of parameter counts. They operate under a singular, unspoken assumption that if we build a sufficiently intelligent model, it will naturally solve our complex business problems. But as production-grade AI agents transition out of research labs and into highly integrated systems, we are hitting a structural wall. A brilliant brain is fundamentally useless if it possesses no hands to manipulate the digital world, no guardrails to boundary its actions, and no memory system to learn from its immediate failures. As we navigate the current landscape of agentic systems, a new realization has swept through the elite ranks of systems engineering. The real differentiator in software automation is no longer the model itself. The model has become a commodity, a high-performance engine that has plateaued in raw semantic capability. The true battleground, and the discipline that separates fragile proof of concepts from reliable production software, is harness engineering. To understand why this shift is happening, we must first confront a fundamental truth about how modern software agents interact with code bases and enterprise workflows. When you ask a raw, unharnessed language model to solve a complex coding issue in a repository containing millions of lines of code, you are asking a stateless, non-deterministic probability engine to perform a task that requires stateful, deterministic precision. Even if the model has a context window large enough to ingest your entire repository, it lacks the execution context to understand if its proposals actually work. It thinks in tokens, not in system states. It produces beautiful, plausible-sounding code that frequently fails to compile, violates repository invariants, or introduces silent security vulnerabilities. This is the execution gap. The raw model cannot run your test suite, it cannot check your linter, and it cannot observe the runtime behavior of its changes. When left to its own devices, a model will suffer from early stopping, fail to decompose complex tasks, and run into severe context drift as its interaction history grows. Harness engineering is the discipline of designing the systems, constraints, and feedback loops that wrap around these models to make them reliable in production. The harness is the complete infrastructure that governs how the agent operates. It is the workspace sandbox, the state manager, the tool orchestrator, the verification pipeline, and the security guardrails. Without a robust harness, an agent is just a demo. With a harness, it becomes a predictable, autonomous software contributor. Let us explore why model capability is no longer enough to build reliable software agents. To do this, we must examine the physical and cognitive limits of modern deep learning architectures. Large language models are autoregressive token predictors. They generate text by calculating the probability of the next token based on the sequence of tokens that came before. This architecture is incredibly powerful for semantic understanding, translation, and synthesis, but it is fundamentally limited when applied to tasks requiring logical consistency over long horizons. One of the most persistent issues we face in agentic workflows is context compression and attention dilution. While modern models boast context windows spanning millions of tokens, their actual retrieval accuracy and attention density are highly non-uniform. When a model is flooded with a massive codebase, its attention degrades. It struggles with what researchers call the lost-in-the-middle phenomenon, where key details located in the middle of a massive context block are systematically ignored. More importantly, as an agent performs multiple actions in an iterative loop, the prompt grows. The model must process its previous attempts, the tool outputs, the error messages, and the user instructions. This compounding history introduces noise, causing the model to lose track of its original goal and begin hallucinating or repeating its mistakes. Furthermore, raw models are stateless. Every time you invoke an LLM API, the model starts with a blank slate. It does not remember the file it edited 10 seconds ago, nor does it understand the systemic consequences of that edit. In a traditional software development environment, state is maintained in the developer's working memory, their local file system, their version control history, and their running application processes. A raw model has none of these. If we do not explicitly build a state management system outside of the model, the agent cannot maintain a coherent mental model of the system it is modifying. There is also the fundamental problem of verification. A software developer does not simply write code and push it straight to production without looking at it. We write code, run it locally, observe compiler warnings, execute tests, inspect log outputs, and manually verify the behavior. We operate within a tight feedback loop. A raw model accessed through a standard API has no built-in feedback loops. It has no physical connection to a computer, no compiler, and no test runner. When it emits a code change, it has no way of knowing if that change introduced a syntax error or broke a critical database migration. Expecting a model to write perfect code on the first attempt without any verification mechanism is a statistical impossibility for any non-trivial task. This brings us to our second foundational concept, which we can express as a core engineering equation: agent equals model plus harness. To build an agent that can reliably operate in the real world, we must view the agent not as an LLM, but as a composite system. In this equation, the model is the engine, but the harness is the chassis, the transmission, the fuel injection system, and the steering wheel. The model provides the raw cognitive force, the semantic reasoning, and the ability to map natural language to potential actions. The harness provides the environment, the structure, the rules, and the feedback loops that turn that raw reasoning into reliable, verified outcomes. Let us break down the anatomical components of this harness. A robust harness consists of 4 primary layers: the workspace layer, the state management layer, the tool and action orchestration layer, and the verification layer. The workspace layer is the sandbox in which the agent lives. It must be isolated, reproducible, and reflective of the real production environment. In a coding context, this workspace is typically a containerized environment with access to a specific branch of a Git repository, a local file system, and the necessary language runtimes. The harness must carefully manage this workspace, ensuring that any modifications made by the model are isolated from production systems and can be easily rolled back if something goes wrong. The state management layer is responsible for tracking the agent's internal and external state across long horizon executions. It maintains the agent's current task list, its historical trajectory, its memory of previous attempts, and its synchronization with the workspace. Rather than relying on the model to remember everything in its active context, the harness acts as the external hard drive of the agent's cognition. It serializes the state, prunes unnecessary history, compresses previous interactions into concise summaries, and structures the context window so that the model always receives a clean, high-density representation of the current system state. The tool and action orchestration layer provides the agent with its hands. This layer exposes specific capabilities to the model, such as reading a file, writing a patch, running a terminal command, searching a database, or invoking an external API. Crucially, the harness does not allow the model to execute these tools directly and unconditionally. Instead, the harness acts as an intermediary runtime. When the model emits a tool call, the harness intercepts it, validates the parameters against strict schemas, checks security permissions, executes the tool in a safe sandbox, captures the output, and formats that output in a way that the model can easily consume. The verification layer is the nervous system of the harness. It is the set of sensors and quality gates that validate the agent's progress. After the model performs an action, the verification layer runs tests, executes compilers, runs security scanners, and evaluates the semantic correctness of the changes. If a test fails, the verification layer does not throw an exception and crash. Instead, it captures the exact failure logs, formats them into a clean, educational feedback loop, and presents them back to the model, guiding the agent's next attempt. The model is allowed to make mistakes, but the harness ensures those mistakes are caught, understood, and corrected before any code is merged. When we look at modern autonomous systems like Claude Code or highly effective enterprise coding agents, we realize that almost 98% of the engineering effort goes into building this harness, while only 2% is spent on selecting or prompting the model. The harness transforms a stochastic model into a deterministic, reliable software system. It creates a custom runtime environment where the model is treated as a highly capable but inherently fallible CPU, and the harness is the operating system that schedules its tasks, manages its memory, and controls its access to peripheral devices. To truly appreciate the necessity of harness engineering, we must examine how our industry evolved to this point. The journey from early language model integrations to modern harness-driven architectures is a story of moving from stochastic art to disciplined, deterministic software engineering. The first major era, spanning roughly from late 2022 through 2024, was the era of prompt engineering. In this phase, developers interacted with models primarily through text-based chat interfaces or raw API wrappers. We believed that the key to unlocking AI capability lay in finding the perfect combination of words, roles, and instructions. We spent countless hours writing elaborate system prompts, instructing the model to act as a world-class staff engineer, and using semantic magic words to coerce it into behaving predictably. We relied on few-shot examples, chain-of-thought instructions, and highly structured markdown templates. However, we quickly discovered that prompt engineering is incredibly fragile. It is an art, not a science. A prompt that worked beautifully on one version of a model would completely fail when the model provider released a minor update to the weights. Even within the same model version, non-deterministic output variance meant that a prompt could succeed 9 times out of 10 and catastrophically fail on the 10th. We had no formal way to test these prompts, no mechanisms to enforce safety, and no ability to scale these systems to complex, multi-step workflows. We were trying to steer a wild horse using only our voice, without any reins. This frustration led to the second phase, which we can call the era of context engineering, dominating much of 2024 and 2025. In this era, we realized that the model needed more than just instructions. It needed data. We focused on retrieval-augmented generation, vector databases, semantic search, and dynamic context packing. We built complex pipelines to split source code, documentation, and enterprise databases into chunks, embed them, and retrieve the most relevant pieces to stuff into the model's active context window. Context engineering was a significant step forward, but it was still fundamentally passive. It assumed that if we provided the model with the right reading material, it would solve the problem. The context layer was still stateless and one-way. We would gather information, bundle it into a massive prompt, send it to the model, and hope for a high-quality response. But we still lacked active control loops. The model could not interact with its environment, modify its inputs based on execution feedback, or safely run the code it generated. We had given the horse a map, but we still hadn't given it a path, nor had we built a carriage for it to pull. This brings us to the modern era of late 2025 and 2026, the era of harness engineering. In this current paradigm, we have stopped treating the model as an oracle that yields completed answers in a single massive leap of inference. Instead, we treat the model as a highly volatile component within an active, stateful, feedback-driven runtime system. We no longer write prompts that say, write a complete, bug-free Python script that implements this feature. Instead, our software systems instantiate a structured harness that guides the model through a series of microtasks. The harness tells the model, write a single module, compile it, run these specific unit tests, read the compiler errors, modify the code to address those errors, and do not proceed until the compiler reports 0 warnings. We have shifted our focus from optimizing the input string to optimizing the execution environment. We build robust state machines, implement POSIX-compliant sandbox runtimes, design semantic memory layers, and enforce strict, code-defined guardrails. Prompting has become a minor implementation detail. The real value is in the software architecture we build around the model. To successfully design these modern systems, we must master 2 key pairs of mental models. The first pair represents the mechanical nature of our control loops, feed-forward versus feedback. The second pair represents how we enforce authority and validation, computational versus inferential control. Let us dissect these models one by one, as they form the theoretical bedrock of all harness engineering. Let us start with the distinction between feed-forward and feedback controls. This concept is borrowed directly from classical control systems theory in mechanical and electrical engineering. In any system where you are trying to steer a variable toward a desired target under conditions of uncertainty, you can control the system either before it acts, which is feed-forward, or after it acts, which is feedback. Feed-forward controls are proactive. They are designed to anticipate errors, restrict the space of possible behaviors, and guide the agent toward correct patterns of execution before it ever generates a single token or invokes a tool. In a coding agent harness, feed-forward controls are the rules, constraints, priors, and architectural guidelines that we build into the agent's environment. A prime example of a feed-forward control is the structural configuration of files like agents.md or workspace rule definitions. These files are not just passive documentation. They are highly structured, mechanical constraints that are automatically parsed by the harness and injected into the agent's context. They establish rigid repository invariants. For example, a feed-forward rule might state that all database queries must use a centralized query builder package rather than hand-rolled raw SQL strings, or that any new API endpoint must include a corresponding integration test in a specific folder. Other feed-forward mechanisms include strict schema validation. When an agent is preparing to make a tool call, the harness can enforce rigid JSON schemas that define exactly what parameters are allowed. If the agent attempts to use an invalid argument, the harness blocks the call at the client boundary before it ever hits the operating system or the network. Feed-forward controls reduce the state space of possible agent behaviors, making it far easier for the model to succeed on its first attempt because we have mathematically narrowed the boundaries of what is permissible. However, feed-forward controls can never be perfect. In complex, dynamic software environments, we cannot anticipate every possible edge case, error, or failure mode. This is where feedback controls become essential. Feedback controls are reactive. They are sensors that observe the output of the agent's actions, analyze the deviation from the desired state, and feed that error signal back into the system to allow the agent to self-correct. When a coding agent edits a file, a feedback-driven harness does not simply accept the edit and ask the user for approval. Instead, the harness immediately activates its sensor suite. It invokes the language compiler, runs the linter, executes the test runner, and analyzes the diff. If the linter reports a code style violation, or if a unit test fails, the harness captures this exact feedback. It wraps the error output in a structured, diagnostic message and delivers it back to the agent in a new control cycle. The feedback message might say, "Your edit to user service caused 2 unit tests in the authentication suite to fail with a null pointer exception. Here is the stack trace. Please analyze this feedback and modify your patch to resolve the issue." By setting up these automated feedback sensors, we allow the agent to iterate, debug, and refine its work autonomously, completely shielding the human developer from the noise of intermediate runtime errors. A well-designed harness uses a delicate balance of feed-forward guides to keep the agent on the right track and feedback sensors to catch it and steer it back when it inevitably slips. Now let us examine our second pair of mental models: computational versus inferential control. This distinction is critical because it defines how we validate the actions of our agents and how we enforce system boundaries. It represents the division between classical deterministic software engineering and modern probabilistic AI engineering. Computational control refers to validation and enforcement mechanisms that are written in traditional deterministic code. These are rules that can be expressed as Boolean logic, regular expressions, AST parses, type checkers, and compiler assertions. Computational controls are absolute, fast, and secure. They do not rely on an LLM to judge whether something is correct. They use the deterministic guarantees of the CPU. For example, when we want to ensure that an agent does not delete a critical production database directory, we do not write a system prompt saying, "Please do not delete the production database." That would be a soft, probabilistic guide, highly vulnerable to prompt injection or model hallucination. Instead, we use computational control. We run the agent's shell environment in a container with a read-only root file system, or we configure the host operating system's file system permissions so that the agent's process literally does not have the right access keys to that directory. If the agent attempts a command like remove recursive on that path, the operating system kernel blocks it with a permission denied error. The harness catches the system error and reports it to the agent. This is computational control. It is binary, unyielding, and fail-safe. Similarly, we use computational control for code validation. We run abstract syntax tree parsers to ensure that the code the agent generated is syntactically valid before we even attempt to write it to disk. We use static analysis tools like ESLint or SonarQube to structurally verify that no deprecated API functions are being introduced. These computational checks run in milliseconds, cost 0 tokens, and provide absolute certainty. However, software engineering is not entirely mechanical. There are many aspects of development that cannot be verified by a compiler or a file permission system. How do we verify that a newly generated UI component looks visually appealing? How do we ensure that a pull request description is coherent, accurate, and professional? How do we verify that a refactored class is actually more readable and maintainable than the original, or that its architectural design aligns with our team's subjective coding philosophy? These are semantic, qualitative questions. Deterministic code cannot parse them. This is where we must employ inferential control. Inferential control uses specialized, highly targeted language models, often running fast, low-latency reasoning engines like DeepSeek R1 or O3 Mini, to act as judges, routers, and evaluators within the harness. In an inferential control setup, the harness uses the model not to generate the main code, but to evaluate the work of the primary agent. For instance, after the primary coding agent generates a refactored module and passes all computational compilation checks, the harness routes the code diff and the original requirements to a separate, specialized critic model. This critic model runs a structured evaluation prompt, analyzing the changes for anti-patterns, security vulnerabilities, or logical mismatches. It returns a structured critique, which the harness can use to approve the change or send it back to the primary agent for another iteration. Inferential control allows us to build semantic guardrails and qualitative validation steps directly into our automated pipelines. We can use it to dynamically route tasks, translate natural language instructions into precise programmatic goals, and perform sophisticated risk assessments on the actions the agent proposes. The magic of high-performance harness engineering lies in how we layer these four concepts. We build systems that combine computational feedforward schemas to restrict what the agent can attempt, inferential feedforward models to prepare the perfect contextual landscape, computational feedback loops to verify compilation and execution, and inferential feedback models to evaluate code quality, style, and semantic correctness. When these layers are misconfigured or poorly balanced, we encounter one of the most common and destructive failure modes in modern agentic systems: the doom loop. A doom loop occurs when an agent gets stuck in an infinite, unproductive cycle of self-correction. Imagine an agent attempting to fix a complex bug in a codebase, proposes a patch. The harness executes a computational feedback loop by running the test suite. The test fails. The agent reads the failure log, but because it doesn't fully understand the underlying system architecture, it makes a slight, superficial modification to its patch and tries again. The test fails again. This cycle repeats endlessly. The agent continues to modify the same line of code over and over, trying different variations of syntax, while completely missing the structural architecture issue that is actually causing the test to fail. It burns through millions of tokens, runs up a massive API bill, and achieves absolutely nothing. To prevent doom loops, a robust harness must build in dynamic escape hatches and progressive escalation policies. First, the harness must strictly limit the number of feedback iterations allowed for a single task. If an agent cannot pass a test suite after 3 or 4 attempts, the harness must intervene. It should not simply let the agent keep trying. Instead, the harness can perform a diagnostic intervention. It can run a wider, semantic search of the codebase to bring in different context files, reset the workspace to a known good state, spin up a specialized diagnostic subagent to analyze the failure from a high level, or gracefully halt execution and escalate the issue to a human engineer with a detailed report of the attempts and the specific failure patterns observed. Another powerful mechanism to prevent doom loops is semantic state tracking. The harness can monitor the similarity of the code modifications proposed by the agent across iterations. If the cosine similarity of successive patches remains extremely high, or if the agent is repeatedly editing the exact same character offsets, the harness detects that the agent has plateaued. It can then inject a strong inferential prompt telling the agent, "You are stuck in an iterative loop making the same change. Step back, reanalyze your assumptions, look at these other utility files, and propose a completely different structural approach." As we conclude this first fundamental chapter of our masterclass, it is vital to internalize the mindset shift that is required to build these modern systems. As software engineers entering the agentic era, we must transition from writing code ourselves, and even from writing prompts for AI to write code, to designing the complex machines that govern how AI writes code safely and reliably. We must stop viewing the language model as a magical black box that will solve our problems if we just ask it nicely. We must view it as a powerful, stochastic, and highly volatile computing core. Like any advanced processor, it requires a robust, well-architected motherboard to function. It needs power delivery, clock synchronization, system buses, and interrupt handlers. Harness engineering is the construction of that motherboard. By mastering the core equation of agent equals model plus harness, understanding the structural limitations of raw models, navigating the historical evolution from simple prompts to active runtimes, and applying the mental models of feed-forward, feedback, computational, and inferential control, we equip ourselves to build systems that do not just generate code, but reliably, predictably, and securely ship software. To build a software agent that can reliably operate inside a complex codebase, we must move beyond basic prompt design and enter the domain of system architecture. In this second chapter of our masterclass, we will focus entirely on the design of the harness itself. We will dissect the blueprint of a production-grade execution environment, exploring how to structure the internal loop that drives the agent, how to manage the vast sea of context it interacts with, how to enforce deterministic boundaries, how to design self-correction feedback mechanisms, and how to safely integrate these systems with existing human developer workflows and CI/CD pipelines. Let us begin by exploring the core engine of harness execution, the steering loop. In standard software development, we are used to deterministic control flows. A program starts at an entry point, executes a sequence of instructions, branches based on conditional statements, and terminates. An agentic system, however, operates within a dynamic, stateful control cycle. This cycle is responsible for orchestration, state management, and execution monitoring. At the heart of the steering loop is the orchestration mechanism. Early agent designs relied on simple loop paradigms like react, reasoning, and action, where the agent generates a thought, invokes a tool, reads the observation, and repeats. While this works for simple search tasks, it completely breaks down in multi-step software engineering workflows. When an agent is tasked with implementing a new feature, it cannot simply live in a reactive, one-step-at-a-time loop. It needs a structured execution plan. Modern harnesses use a stateful, DAG-based orchestration engine. When a task is received, the orchestrator first invokes a specialized planning loop. This planning loop does not write code. Instead, it generates a directed acyclic graph of subtasks. Each node in this graph represents a specific bounded objective, such as mapping the existing data flows, writing a test suite, implementing the interface, refactoring the implementation, or running validation checks. The edges of the graph define the dependencies between these tasks. The steering loop then acts as a state machine that executes this graph. It maintains a centralized execution state, scheduling nodes whose dependencies have been fully resolved. For each active node, the orchestrator manages a localized control cycle. This cycle consists of 4 distinct phases: intent formulation, action execution, result ingestion, and state transition validation. During the intent formulation phase, the orchestrator prepares the execution context for the node, pulling in the relevant subtask definition, current repository state, and previous execution artifacts. It passes this context to the model, which emits a desired action, such as editing a file or executing a terminal command. The harness then intercepts this action and passes it to the action execution layer. The action is executed in a highly sandboxed, isolated environment. Once the action completes, the result ingestion layer captures the output, standardizing it into a common data envelope. This envelope includes the process exit code, the standard output, the standard error, and any file system diffs generated during the action. Finally, the state transition validation layer evaluates the result. It uses a series of computational and inferential checks to determine if the subtask node has been successfully resolved. If the node is validated, the orchestrator transitions its state to complete, updates the master execution graph, and schedules the next dependent task. If the node execution fails, the orchestrator does not crash. Instead, it triggers a localized recovery loop, dynamically modifying the graph or attempting a corrective action. Managing state throughout this complex steering loop is one of the most difficult engineering challenges in harness design. Because the model itself is stateless, the harness must serve as the source of truth for the system's state. If we fail to manage the state correctly, the agent will quickly suffer from state drift, where its internal understanding of the workspace diverges from the physical reality of the file system and container environment. To solve this, the harness must maintain a 2-part state model: the workspace state and the cognitive state. The workspace state is deterministic and physical. It tracks the exact state of the Git repository, the modified file paths, the active processes, and the file system diffs. Every time the steering loop transitions, the harness performs a lightweight scan of the workspace, checking Git status and computing file hashes to detect any changes made by the agent or external processes. The cognitive state, on the other hand, is semantic and hierarchical. It tracks the agent's current progress through the task graph, its active hypothesis, its memory of previous failed attempts, and the accumulated knowledge about the codebase. The harness serializes this cognitive state into a structured JSON envelope, completely separate from the conversation history. This allows the harness to dynamically prune, summarize, or reconstruct the prompt payload sent to the model on each control cycle, ensuring the agent's active context remains clean, focused, and free of historical noise. Now, let us turn our attention to the physical architecture of the context layer. If the steering loop is the engine of the agent, context is the fuel. However, in modern repository environments, we face a severe resource constraint: the token window of our models and, more importantly, the dilution of model attention. If we dump an entire enterprise repository into the context window, the model will struggle to find the needle in the haystack, and the execution latency and API costs will skyrocket. We need a sophisticated context architecture that relies on structured documents, dynamic knowledge bases, progressive disclosure, and semantic compaction. The first pillar of a clean context architecture is a structured project guide. typically placed in the root of the repository as a file named agents.md. This file serves as the onboarding manual and operational boundary for any agent entering the workspace. It is not written in free-form prose. Instead, it uses a highly structured, machine-readable format that the harness automatically parses and injects into the agent's root system prompt. The agents.md file defines several critical components of the workspace. It details the project's system architecture, explaining the directory structure, the core technology stack, the entry points of the application, and the primary data flows. It lists the repository invariants, which are the golden rules that the agent must never violate, such as using specific linting rules, adhering to strict naming conventions, or utilizing centralized utility classes for database access. It also defines the testing philosophy, explaining where tests live, how to execute the test runner, and how to write new unit and integration tests. By codifying this information in agents.md, we create a highly stable, repository-specific feed-forward control. The harness reads this file, validates its structure, and forces the model to acknowledge these guidelines on every single turn. This completely eliminates the need to write custom system prompts for different repositories. The agent's core model remains generic, while its behavioral boundaries are dynamically configured by the target workspace itself. Beneath the agents.md layer sits the dynamic knowledge base. An agent cannot rely purely on file reading tools to discover the codebase. Reading files one by one is incredibly slow and expensive. The harness must build and maintain an active structural map of the repository. This map is constructed using a hybrid approach that combines tree-sitter AST parsers with vector and graph databases. When the harness first initializes inside a codebase, it performs an offline structural index. It uses tree-sitter to parse every source file, extracting the class definitions, function signatures, dependencies, and doc strings. It builds a hierarchical symbol tree, mapping how different modules and functions import and call one another. This structural index is stored as an active in-memory graph. At the same time, the harness computes vector embeddings for individual semantic chunks of the codebase, storing them in a local, fast vector database. When the agent is tasked with a modification, the harness does not wait for the agent to ask to see files. Instead, it runs an automated context retrieval pipeline. It analyzes the agent's current objective, queries the vector database for semantically similar code snippets, and traverses the AST call graph to pull in the signatures of dependent modules. It bundles this retrieved structural data into a high-density, read-only system map, presenting it to the agent as a specialized context block. To present this context efficiently without overwhelming the model, the harness must employ a strategy of progressive disclosure. Progressive disclosure is the practice of only showing the agent the absolute minimum detail it needs to perform its current step, while providing a clear path to request more detail as needed. Imagine an agent trying to fix a bug in a complex authentication module. The harness does not immediately feed the entire source code of the authentication module and all its imports into the context window. Instead, it starts by disclosing a high-level file tree of the target directory. When the agent identifies a specific file of interest, the harness discloses only the file's outline, its class hierarchy, public methods, and function signatures, using an AST-generated summary. Only when the agent explicitly requests to view or edit a specific method does the harness disclose the full implementation of that localized block of code. This lazy loading strategy ensures that the agent's active memory is never cluttered with irrelevant lines of code. It preserves the model's high-density attention for the exact lines it is modifying, dramatically reducing compilation errors and logic slips. Even with progressive disclosure, the history of an agent's interaction during a long-horizon task will inevitably grow. As the agent runs tests, encounters errors, edits files, and reasons through problems, the conversation history accumulates thousands of tokens of redundant or low-value information. If we pass this raw history back to the model on every turn, we will encounter extreme latency and context drift. We must implement active compaction strategies. Compaction is the process of structurally pruning and distilling the agent's active context window. The harness runs a background worker on every turn of the steering loop, monitoring the token count of the conversation history. When the history crosses a specific threshold, the compaction engine is activated. The compaction engine does not just slice off old messages. Instead, it performs a semantic distillation. It groups previous message exchanges into logical execution epochs. For each completed epoch, the engine invokes a lightweight, fast model to generate a highly compressed, structured summary of what occurred. The summary details the original hypothesis, the actions taken, the observed feedback, why the approach succeeded or failed, and the final state of the files involved. The harness then replaces the raw, multi-turn messages of that epoch with this single high-density summary block. If the agent encountered 10 compilation errors and ran the compiler 10 times, the raw compiler logs are completely discarded. They are replaced by a single line in the summary. Compilation failed 5 times due to an imported type mismatch, which was resolved in commit X by updating the import path. This progressive compaction keeps the context window lean, ensuring that the model is always operating at peak cognitive efficiency. Let us now move to the third major structural component of the harness, the constraint harness. This is our feed-forward defense system. Its sole purpose is to prevent the agent from making catastrophic mistakes, generating invalid outputs, or violating system boundaries before any actions are executed. It is the combination of rules, guardrails, schemas, and permission systems. The first line of defense is schema enforcement. When we design tools for our agents, such as tools to read files, search directories, write code patches, or run terminal commands, we must never allow the model to invoke these tools using free-form natural language. We must define strict, typed schemas for every single tool. In modern harness design, we use frameworks like Agentic or TypeScript type definitions to declare these schemas. When the agent wants to invoke a tool to edit a file, the harness does not accept a prompt like, "Please change line 24 of server.js to use port 8080. Instead, the tool schema requires a structured JSON payload containing the target file path, the exact line range to modify, the expected original code block, and the new replacement code block. When the agent emits a tool call, the harness parses the JSON payload and validates it against the schema. If the payload violates the schema, for example, if a required field is missing, or if an argument is of the wrong data type, the harness immediately rejects the call. The rejection is handled locally by the harness runtime, returning a clean, programmatic error message to the model before any execution occurs. This prevents the agent from attempting ill-formed commands and teaches it to use the tool APIs with mathematical precision. Beneath the schemas lie the active guardrails. Guardrails are real-time, high-speed validation pipelines that inspect the inputs and proposed outputs of the agent. They run both statically and dynamically. Static guardrails use deterministic code, such as regular expressions, abstract syntax tree parsers, and type checkers, to evaluate the code patches proposed by the agent before they are written to disk. For example, if an agent is editing a TypeScript file, the harness runs a lightweight AST parser on the proposed code change. If the parser detects a syntax error, such as an unclosed curly brace or an invalid keyword, the guardrail blocks the edit. It returns the syntax error directly to the model, instructing it to fix the structure before applying the change. Dynamic guardrails, on the other hand, monitor system-level behaviors. They set absolute limits on execution parameters. A robust harness will enforce limits on the maximum file size an agent can write, the maximum number of files it can modify in a single turn, the maximum execution time of any terminal command it invokes, and the total token budget allocated to a given task. If an agent goes rogue and attempts to write a 10 megabyte log file, or if it triggers an infinite loop in a script that runs for several minutes, the dynamic guardrail automatically terminates the process, safeguarding the host system and the API budget from exhaustion. While schemas and guardrails protect the application layer, we must also enforce absolute security at the system layer. This is the domain of the permission system and sandboxing runtime. We must operate under the principle of least privilege. An autonomous agent must never be trusted with raw, unconstrained shell access to a production environment or a development machine. A professional harness runs the agent's execution environment inside a highly isolated, containerized sandbox. This sandbox is typically built using virtualization technologies like lightweight Docker containers, gvisor microkernels, or WebAssembly micro-runtimes. This environment is completely detached from the host operating system. Within this sandbox, the harness enforces a strict permission model. The file system is configured with fine-grained access control lists. The agent is granted write permission only to the specific directory containing the target codebase. Critical system configuration directories, environment variables, SSH keys, and network configuration files are completely hidden or mounted as read-only. Furthermore, network access within the sandbox is highly restricted. The sandbox is running behind an egress filtering firewall that blocks all outbound traffic by default. The agent is allowed to communicate only with explicitly whitelist domains, such as the package manager's NPM, pip, or cargo, and the specific APIs required for its tools. If the agent is compromised by a malicious dependency or a prompt injection attack, the firewall prevents it from exfiltrating sensitive source code or executing a reverse shell to a remote command and control server. The sandbox permission system ensures that even if the agent's cognitive engine is entirely hijacked, its physical reach is completely contained within a harmless digital jail. Despite our best feed-forward constraints, an agent operating in a complex, real-world repository will inevitably write buggy code, break dependencies, or encounter execution failures. The true hallmark of an elite agent is not that it never makes mistakes, but that it possesses the feedback loops and self-correction mechanisms to discover and fix those mistakes autonomously. This is where we must design robust verification, evaluation, and recovery patterns. The first step in self-correction is the design of effective verification loops. When an agent completes an edit to a file, the harness must immediately trigger an automated verification sequence. This sequence must be completely transparent to the user. It is an internal dialogue between the harness and the agent. The verification sequence begins with static analysis. The harness runs the workspace linter and type checker on the modified files. If the linter reports style violations, or if the type checker reports type safety failures, the harness captures these outputs. It does not output raw, unformatted console text to the model. Instead, it parses the diagnostic errors into a structured envelope that maps each error to the exact file path, line number, and character offset, alongside an explanation of the rule that was violated. If the static analysis passes, the verification sequence moves to dynamic execution. The harness invokes the target test runner. However, running the entire test suite of a massive application on every single edit is incredibly slow and inefficient. To optimize this, the harness uses test impact analysis. The harness analyzes the import graph and the git diff to identify the exact subset of unit and integration tests that could potentially be affected by the agent's changes. It executes only this highly targeted subset of tests. If the tests pass, the verification is successful. If any tests fail, the harness captures the test failures, extracts the relevant assertion errors, stack traces, and console outputs, and formats them into a clean debugging context. This structured feedback is then presented to the agent as a new execution instruction. The harness tells the agent, "Your change compiled successfully, but 2 unit tests failed. Here are the specific failures. Please analyze the stack traces, inspect the state of the system, and propose a corrective patch." This creates an automated, tight loop of generation, verification, failure analysis, and correction, allowing the agent to refine its work until it passes all quality standards. To make this feedback loop truly effective, we must combine our computational verification with an active semantic evaluation layer. While tests and linters verify that the code compiles and runs, they cannot evaluate whether the code is written cleanly, whether it follows architectural best practices, or whether it introduces security vulnerabilities. To solve this, the harness implements an internal evaluation loop. Before a task is marked as complete, the harness routes the code changes to an independent evaluation module. This module runs a highly specialized, fast reasoning engine that acts as an automated code reviewer. The evaluator model is programmed with a set of rigorous evaluation rubrics, which are aligned with the guidelines established in the project's agents.md file. It reviews the diff, looking for common code smells, duplicate code, inefficient algorithms, missing error handling, or exposed secrets. It grades the changes on a scale of correctness, maintainability, and security. If the evaluator model identifies major issues, it generates a structured review report containing specific line-by-line critiques and actionable improvement suggestions. The harness treats this report as a failing feedback signal. It resets the workspace state, presents the evaluator's critique to the primary agent, and directs it to revise the implementation to address the feedback. This peer review architecture ensures that the agent's work is held to the same rigorous stylistic and architectural standards as a human developer's code. But what happens when the agent's self-correction loop stalls? What happens when the agent is stuck, unable to pass a compilation check, or running into a persistent test failure? If we do not design robust recovery patterns, the agent will collapse into the destructive doom loops we discussed in Chapter 1, or simply freeze, wasting valuable processing time. To prevent this, the harness must implement a structured, multi-tier recovery pattern. The first tier of recovery is backtracking. The harness maintains an active checkpoint restore ledger of the workspace. Every time the agent begins a new subtask node in its execution graph, the harness takes a lightweight snapshot of the codebase, typically by creating a temporary Git branch or staging the current files. If the agent attempts to fix a test failure and fails to resolve it after a predefined number of attempts, say 3 iterations, the harness triggers a backtrack. It completely discards the agent's messy, iterative edits, rolls back the file system to the clean checkpoint at the start of the subtask, and resets the agent's conversation history for that epoch. It then reinitiates the task, but with a critical modification. It injects a high-level diagnostic instruction, directing the agent to abandon its previous approach, analyze the system from a different angle, and try a completely new architectural strategy. If backtracking fails, the harness escalates to the second tier of recovery: subagent dispatching. The harness can dynamically spin up a specialized, highly focused subagent whose sole task is to debug the specific failure blocking the primary agent. This diagnostic subagent is initialized with a clean, isolated context window. It is given only the failing file, the test output, and the compiler logs. Because it is free from the historical noise and cognitive baggage of the primary agent's long-horizon conversation, the diagnostic subagent can analyze the problem with fresh cognitive capacity. It works in its own micro-sandbox to find a working solution, writes a localized patch that resolves the compilation or test failure, and passes the verified patch back to the primary orchestrator. The primary harness then applies this verified patch to the main workspace, updates the primary agent's state, and allows it to proceed with the wider task. This modular division of labor allows the system to easily overcome localized obstacles that would otherwise derail a single monolithic agent. Finally, we must examine how to connect this highly advanced, autonomous harness to the real-world software delivery lifecycle. A software agent does not operate in a vacuum. It must collaborate with human developers, integrate with enterprise continuous integration and continuous deployment pipelines, and adhere to strict organizational quality gates. This is the domain of CI/CD integration, human-in-the-loop protocols, and approval workflows. Let us first design the CI/CD integration. In a mature engineering organization, agents are not allowed to push code directly to main production branches. They must follow the exact same pull request and review workflows as human engineers. The harness acts as the bridge between the agent's sandbox and the enterprise version control system, such as GitHub or GitLab. When an agent is assigned a ticket or a bug report, the harness automatically creates a new, isolated Git branch from the latest development head. The agent performs its work, runs its verification loops, and refines the code inside its sandboxed workspace. Once the harness successfully validates the changes, meaning the code passes all local tests, type checkers, and internal evaluation rubrics, the harness prepares the commit payload. The harness does not simply push a raw, undocumented commit. It uses its internal state manager to compile a comprehensive, highly structured pull request description. This description details the original issue, explains the technical root cause that was identified, outlines the architectural changes that were made, lists the specific files that were modified, and provides a detailed matrix of the test suites that were executed and passed. The harness then pushes the branch to the central repository and programmatically opens a pull request. This action automatically triggers the organization's standard CI/CD pipelines. The CI/CD system runs its own independent build, executes the complete enterprise integration and end-to-end test suites, runs security scanners like SNYK or SonarCube, and generates static analysis reports. If the CI/CD build fails, the harness remains active. It listens to the CI/CD webhook events. If a build failure is detected, the harness automatically pulls the external CI/CD logs back into the agent's workspace, wakes up the agent, and directs it to fix the issues on the branch. This creates a fully automated integration loop, where the agent continuously refines its branch until the enterprise CI/CD pipeline greenlights the build. This brings us to the critical concept of human-in-the-loop, or HITL orchestration. No matter how advanced our models and harnesses become, there will always be situations where the agent requires human guidance, clarification, or explicit authorization. A professional harness must design elegant, low-friction break glass protocols and interactive approval workflows. We must never design a system where the agent is allowed to execute high-risk actions without explicit human-in-the-loop validation. High-risk actions include executing arbitrary, non-sandboxed shell commands, importing new external third-party dependencies, refactoring core security or cryptographic modules, or modifying files outside of the designated project workspace. To manage this safely, the harness implements a structured approval gateway. When the agent's steering loop determines that a high-risk action is necessary to complete a task, the orchestrator pauses the execution cycle. It serializes the current state, freezes the sandbox, and generates a structured approval request. This request is delivered to the human engineers through their existing communication channels, such as Slack, Microsoft Teams, or a specialized pull request dashboard. The request is designed to be incredibly easy for a human to review. It does not output raw, confusing terminal logs. Instead, it presents a clear, high-level summary of what the agent is attempting to do, why it is attempting it, and the potential risks involved. For example, if the agent wants to install a new NPM package, the approval message might say, "The agent is requesting to install the library low-es to optimize array manipulation in the user service." This package is widely adopted, has 0 known security vulnerabilities in its current version, and adds approximately 40 kilobytes to the bundle size. Do you approve this installation? The human reviewer is presented with simple, clear options: approve, deny, or redirect. If the human clicks approve, the harness receives the webhook, unfreezes the sandbox, executes the installation, and allows the agent to continue. If the human clicks deny, the harness blocks the action and informs the agent that the installation was rejected due to organizational policy, forcing the agent to find an alternative solution using existing internal utility modules. If the human selects redirect, they can provide a natural language guidance hint, such as, "We do not use Lodash in this repository. Please use native JavaScript ES6 array methods like map and filter instead." The harness injects this direct human feedback straight into the agent's active cognitive context. The agent parses the instruction, adjusts its planning graph, and proceeds down the approved architectural path. This interactive guidance allows a senior engineer to mentor and steer the agent in real time, matching the natural, collaborative flow of a senior developer pairing with a junior engineer. Furthermore, we must design structured review systems for the final code output before it is ever merged. When a human developer reviews an agent's pull request, they must feel an absolute level of trust. If the agent's code is messy, uncommented, or difficult to read, The human reviewer will spend more time refactoring the agent's code than they would have spent writing it themselves. The harness must ensure the agent's output is pristine. To achieve this, the harness runs a final post-processing and polishing pipeline before finalizing any pull request. This pipeline automatically runs code formatters like prettier or black to guarantee perfect, consistent syntax layout. It runs automated documentation generators to ensure all new public methods have clean, accurate JSDoc, JavaDoc, or docstring comments detailing their parameters, return types, and potential exceptions. More importantly, the harness forces the agent to write comprehensive, high-coverage unit tests for any new modules it introduces. The harness verification layer will actively reject the agent's own pull request if the test coverage score of the modified files drops below the repository's established threshold. This ensures that the agent never pushes technical debt into the codebase. Every contribution is fully documented, styled, and covered by robust, automated tests, making the human review process a fast, pleasant, and high-confidence final sign-off. As we conclude this second chapter on harness design, let us take a moment to reflect on the architectural system we have mapped out. We have designed a steering loop that moves beyond simple reactive prompting, utilizing structured DAG task planning, active execution sandboxes, and precise state serialization. We have built a clean context architecture that utilizes structured guidelines like agents.md, dynamic AST-driven knowledge bases, progressive disclosure, and active semantic compaction to keep our models running at peak cognitive efficiency. We have established a robust, feed-forward constraint harness using typed schemas, static and dynamic guardrails, and secure, isolated sandboxes to enforce absolute boundaries and protect our systems. We have designed a state-of-the-art feedback loop that utilizes targeted test impact verification, qualitative peer review evaluation, and multi-tier recovery patterns like backtracking and diagnostic subagent dispatching to allow our agents to autonomously self-correct and overcome complex obstacles. And finally, we have designed a secure, seamless integration into the enterprise software delivery lifecycle using automated pull request generation, dynamic CI/CD webhook loops, and elegant, high-trust human-in-the-loop approval workflows. By constructing this comprehensive harness, we elevate the language model from an unpredictable, stateless text generator into a highly disciplined, productive, and secure autonomous software engineer. We build a system where the AI is empowered to execute complex, long-horizon development tasks with absolute precision, while remaining firmly bound within the safety, quality, and architectural standards of our organization. This is the true power of harness engineering, building the digital machine that turns raw machine learning into reliable, scalable, and enterprise-ready software automation. As we venture deeper into the architecture of modern harness systems, we transition from the general layout of steering loops and validation gates to the advanced, low-level mechanics of enterprise-grade execution environments. To build an agent capable of modifying complex, distributed code bases or orchestrating deep engineering tasks, we must design systems that operate at the intersection of operating systems theory, network security, distributed systems, and real-time observability. In this third chapter, we will dissect the advanced components of harness engineering, detailing the mechanics of sandbox tool orchestration, multi-agent hierarchies, real-time observability, fail-closed security governance, and persistent multi-tiered memory systems. Let us begin with the physical isolation and execution of tools, tool orchestration and sandboxing. In any production environment, Giving an agent access to a shell or tool execution interface is equivalent to granting arbitrary remote code execution permissions to an untrusted actor. If the agent imports a compromised library from a public package registry, or if it falls victim to an indirect prompt injection attack hidden within a repository's documentation, a naive harness will allow the malicious exploit to run with the full system permissions of the host. To mitigate this risk, we must construct a highly sophisticated, multi-layered isolation sandbox. In modern software engineering, the industry standard has moved away from thick, slow virtual machines toward highly optimized, micro-virtualization runtimes. We rely heavily on technologies like Firecracker micro-VMs, gvisor sandbox containers, or specialized WebAssembly micro-runtimes. Let us analyze the system architecture of a Firecracker-based harness sandbox. When an agent session is initialized, the harness boots a dedicated minimalist Linux kernel inside a Firecracker micro-virtual machine. This boot cycle is incredibly fast, taking less than 150 milliseconds, and has a memory footprint of only a few megabytes. The micro-VM runs a stripped-down, read-only root file system containing only the absolute minimum utilities required for the agent to function, such as Git, a basic bash shell, and the runtime compiler or interpreter for the target language. Within this micro-VM, we must virtualize the file system layer to allow safe, fast modifications. We achieve this by utilizing an OverlayFS volume mount. The base layer of the file system, which contains the repository head and the system dependencies, is mounted as read-only. Above this read-only base, the harness mounts a writable temporary file system as an overlay. When the agent attempts to edit a file, the micro-VM kernel intercepts the write operation and performs a copy on write, storing the modification exclusively in the volatile overlay layer. This design provides two massive benefits. First, it ensures that the original base code base is physically protected from accidental destruction. Second, it allows the harness to perform instantaneous rollback operations. If the agent writes a buggy patch that breaks the entire sandbox environment, the harness simply drops the overlay layer and recreates a new one in milliseconds, restoring the system to a clean state without needing a slow reboot cycle. But isolating the file system is only half the battle. We must also isolate the tool calling mechanics themselves. A model does not execute tools. The model emits a sequence of tokens representing a structured command, and the harness must translate that command into a safe, non-interactive system execution. When an agent wants to run a CLI tool, such as compiling code with cargo build or executing a test suite with PyTest, the harness interceptor does not pass the raw command string to a standard shell executor. Doing so would expose the system to shell injection attacks, where the agent might append a semicolon followed by a malicious background script. Instead, the harness uses a non-interactive POSIX wrapping system. It parses the model's requested action, decomposes the command into a structured argument vector, and invokes the execution using system-level fork and exec patterns. It directly controls the process input, output, and error file descriptors. Furthermore, the harness must handle interactive tools that expect terminal input. If the agent runs a tool that prompts for user input, a naive executor will hang indefinitely, waiting for a STIN signal that will never come, wasting valuable processing time. To prevent this, the harness runs the sandbox process inside a pseudo-terminal wrapper, or PTY allocation. The harness monitors the standard output stream of the process in real time. If it detects a blocking input prompt or a standard interactive indicator, the harness intercepts the execution, kills the stalled process, and returns a diagnostic message to the agent. This command required interactive input, which is not supported. Please run the tool using non-interactive flags or configure the environment variables to bypass prompts. We must also implement process lifecycle management. If the agent starts an asynchronous process, such as spinning up a local development database or starting a web server to verify an API endpoint, the harness must track these background processes. It maintains a process registry, mapping the process identifiers, resource consumption, and parent-child relationships. When the agent's main steering cycle completes or transitions to another task, the harness sweeps this process registry. It sends structured system signals, starting with SIGTERM to allow clean shutdown, and escalating to SIGKILL if the process fails to terminate, preventing orphan zombie processes from consuming system resources and leaking memory in the sandbox container. To complete the sandboxing architecture, we must enforce absolute containment at the network layer. A coding agent frequently needs outbound network access to fetch dependencies, query package managers, or communicate with public API endpoints. However, allowing unrestricted internet access exposes the enterprise to severe data exfiltration risks. To solve this, the harness establishes an eBPF-driven network filter at the host namespace boundary. eBPF, or Extended Berkeley Packet Filter, allows us to run sandboxed, high-performance bytecode programs directly within the Linux kernel, monitoring and filtering network packets as they pass through virtual network interfaces. The host firewall is configured with a default deny egress policy. The harness configure rules within the eBPF layer to block all outbound TCP and UDP connections except for a highly strict whitelist. This whitelist is dynamically configured based on the task context. It allows connection only to specific, verified domain names, such as registry.npmjs.org for node.js projects, or pypi.org for Python environments, and redirects all other outbound requests to a local DNS sinkhole. For secure API calls, the harness intercepts all HTTP traffic using a local egress proxy server. This proxy decrypts the sandboxed SSL traffic using a trusted root certificate generated for the session. It inspects the HTTP headers, path parameters, and query payloads of the outbound requests. If it detects signatures of sensitive project files, API keys, or proprietary source code being exfiltrated via post requests to unauthorized endpoints, it blocks the payload, drops the network socket, and flags the session for an immediate security audit. This deep network inspection ensures that even if an agent runs a compromised third-party library, the host enterprise's sensitive data remains absolutely secure. Let us now transition from the execution mechanics of a single agent to the complex coordination of multi-agent systems and sub-agent spawning. As software tasks scale in complexity, relying on a single monolithic agent is no longer viable. A single agent trying to perform architectural design, write code, implement tests, run security scans, and handle deployments will quickly hit cognitive limits, suffer from severe context window saturation, and drop its reasoning fidelity. Modern enterprise harnesses use a multi-agent actor model architecture. Instead of one massive model, we design a network of specialized, highly focused agents that coordinate through structured communication protocols. The primary agent acts as a supervisor or coordinator, and it has the capability to programmatically spawn specialized sub-agents to solve isolated subproblems. Let us analyze the spawning lifecycle of a sub-agent. When the primary coordinator determines that a subtask within its planning graph requires deep, isolated specialization, such as refactoring a database schema or writing an exhaustive suite of unit tests, it emits a spawn subagent tool call. This spawn call is intercepted by the multi-agent orchestrator within the harness. The orchestrator initializes a new, independent subagent runner. This subagent is not spawned inside the primary agent's workspace container. It is allocated its own, completely separate, containerized sandbox, isolated at the OS and namespace level from the coordinator. The orchestrator configures the subagent with a custom-tailored, minimal context. It does not pass the parent agent's conversation history or entire system context. Instead, it provides a precise, bounded initialization payload. This payload contains the specific module file to modify, the target interface, the explicit technical goal, and a highly constrained toolset designed specifically for that subagent's role. For example, a test generator subagent is given read permissions to the source file, write permissions exclusively to the corresponding test folder, and access only to the test runner tool. It has no command line terminal execution tools, no network access, and no file deletion capabilities. Communication between these agents must be highly structured to prevent chaotic, non-deterministic interactions. Agents are not allowed to chat freely with one another in unstructured natural language. Free-form conversational loops between agents lead to cognitive drift, circular logic, and rapid token exhaustion. Instead, the harness enforces a strict message passing protocol over an internal event bus, typically managed using lightweight, in-sandbox message queues like Redis or RabbitMQ. When a subagent completes its assigned task, it packages its output into a structured JSON envelope. This envelope includes a status flag indicating success or failure, a semantic summary of the work completed, the specific file diffs produced, and a list of verification metrics, such as unit test coverage and compilation results. The orchestrator captures this envelope, validates its schema, shuts down the subagent's sandbox container to free host resources, and passes the structured payload back to the primary coordinator as an event observation. The coordinator inspects the structured metrics and decides whether to merge the subagent's code diffs into the main workspace or send a rejection event, forcing a clean spawn cycle with modified instructions. While multi-agent systems are incredibly powerful, they introduce a severe systemic risk: communication storms and cascade failures. If two agents are misconfigured, they can easily get locked in an infinite ping-pong loop, where Agent A asks Agent B for clarification, Agent B responds with a request for more detail, and the two models exchange messages endlessly, generating massive token consumption and skyrocketing costs. To prevent this, the multi-agent harness must enforce active, system-wide governance limits. The orchestrator tracks a centralized token and cost budget for the entire spawn tree. Every subagent spawned inherits a portion of the parent's budget. The depth of the spawning hierarchy is strictly capped, typically allowing no more than 2 or 3 levels of recursion. Furthermore, the harness monitors the messaging frequency on the event bus. If it detects that two agents are exchanging messages at a rate that exceeds safe algorithmic thresholds, or if the semantic similarity of successive messages indicates a non-productive loop, the orchestrator triggers an automatic circuit breaker. It freezes the subagent execution, rolls back the subsandbox, and injects a hard system interrupt into the primary coordinator, forcing it to reassess the architectural approach or halt execution to await human intervention. To manage these complex systems effectively, we must build a deep, high-fidelity observability and logging framework. In traditional software development, observability is achieved by tracking metrics, logs, and traces using tools like OpenTelemetry, Prometheus, and Jaeger. In harness engineering, we must extend these concepts to track the highly complex, non-deterministic internal states of our agents. This is critical for debugging agent failures and managing system entropy. Let us first examine the trace architecture. In a harness system, we do not simply log model inputs and outputs. We must trace every single step of the agent's cognitive trajectory. This is done by mapping our logs to the OpenTelemetry semantic conventions for AI systems, which treats every model invocation, tool execution, and state validation as a distinct span in a hierarchical distributed trace. When a user initiates a high-level task, the harness starts a root span. As the coordinator maps out its plan and executes subtasks, the harness creates child spans for each step of the steering loop. Within a single loop span, we capture metadata with high granularity. The exact model parameters used, the exact system prompt template, the semantic context retrieval queries, the raw prompt sent to the LLM, the raw response generated, the parse tool call parameters, the sandboxed execution stout and stare, the file system diffs, and the final state validation outcome. By structuring our logs as a continuous hierarchical trace, we can visualize the agent's exact decision tree. If the agent fails to implement a feature, an engineer does not have to sift through megabytes of unformatted console text. They can open a tracing dashboard and see a clear graphical timeline of the agent's execution. They can pinpoint the exact moment where the agent made an incorrect logical assumption, see how that assumption led to an invalid tool call, trace how the tool call produced an error, and understand why the agent's subsequent self-correction loops failed to resolve the issue. But observability in agentic systems goes beyond simple logging. We must actively manage system entropy and state drift. In physics, entropy is a measure of disorder in a system. In software engineering, as an agent performs dozens of consecutive edits, compilations, and test runs inside a workspace, the system's entropy naturally increases. State drift is the gradual divergence of the agent's internal cognitive model of the codebase from the physical reality of the sandbox file system. For example, if the agent updates a utility module signature but fails to update an import path in a distant service, and the test suite doesn't immediately catch the error, the workspace state is broken. The agent's next planning steps will be based on a flawed assumption that the codebase is healthy, leading to cascading failures that are incredibly difficult to diagnose. To combat entropy and state drift, the harness implements an automated entropy management and garbage collection system. At regular intervals within the steering loop, typically after every 3 or 4 task transitions, the harness pauses the agent's execution and runs a workspace reconciliation routine. The reconciliation routine is a fast, deterministic scan of the entire sandbox environment. It performs a git status check to detect all modified and untracked files. It parses the modified files using treesitter to rebuild the local symbol graph, verifying that all imports, class interfaces, and method signatures remain structurally coherent across the codebase. Furthermore, the harness monitors the agent's active context window utility ratio. This metric represents the ratio of semantically valuable information inside the context to redundant noise. If the harness detects that the context is flooded with old compiler logs, repeated error traces, or outdated class outlines, it triggers active garbage collection. The garbage collector prunes the conversation history, compresses the historical epochs, and evicts stale symbols from the agent's active memory map. It forces a complete reload of the workspace's structural representation, ensuring that the model starts its next planning turn with a pristine, fully reconciled, and high-fidelity representation of the physical workspace. This continuous reconciliation bounds the system's entropy, preventing the cognitive decay that causes long-running agents to lose their grip on reality and fail. Now let us focus on safety, security, and governance. When designing autonomous agents that operate inside enterprise environments, we must implement a secure by default architecture. We cannot rely on the model's willingness to follow safety guidelines. We must build mathematical, structural systems that enforce absolute safety parameters. This is the domain of fail-closed principles, robust guardrails that avoid YOLO classifiers, and advanced doom loop prevention. Let us first define the fail-closed principle in harness design. In traditional system security, a fail-closed architecture ensures that if a system component fails, runs out of resources, or encounters an ambiguous or unexpected state, the system automatically transitions to its most secure, locked-down configuration. In an agent harness, we apply this principle across all execution boundaries. If the harness's state validation module encounters an unparsable response from the model, or if a tool execution returns an unexpected error format, the system does not attempt to guess the model's intent. It automatically halts all execution, locks the sandbox file system, blocks all network egress, and pauses the steering loop. Similarly, if the harness's security monitors detect any anomalous activity inside the sandbox micro-VM, such as a process attempting to modify permissions of system files, or an unexpected burst of network traffic targeting a non-whitelist IP, the system triggers an instant, fail-closed isolation script. The eBPF kernel filter immediately drops all network packets. The micro-VM container is paused at the hypervisor level, and the orchestrator revokes all tool execution privileges. The harness freezes the entire session state and escalates the event to the enterprise security team with a cryptographically signed trace of the execution. By defaulting to absolute lockdown rather than permissive continuation, we guarantee that no failure or exploit can ever escalate into an enterprise-wide security breach. Another critical safety pattern is the avoidance of YOLO classifiers. The term YOLO classifier refers to the dangerous, naive anti-pattern of using a standard, probabilistic LLM call to evaluate whether a proposed action or file change is safe. For example, a developer might write a prompt saying, "Look at this shell command. If it contains a delete operation, return true. Otherwise, return false." This is a catastrophic engineering mistake. LLMs are probabilistic token predictors. They are subject to semantic confusion, prompt injections, and adversarial exploits. A sophisticated prompt injection hidden inside a benign-looking file could easily bypass this LLM classifier, tricking the model into returning false and executing a highly destructive system command. A secure harness completely replaces these soft, inferential classifiers with rigid, deterministic, and multi-layered validation systems. We use static analysis, signature scanning, and sandboxed validation runtimes instead of probabilistic evaluation. For shell command safety, we use absolute argument parsing and AST-based shell validation libraries. When the agent requests to execute a bash command, the harness passes the command string through a deterministic parser like bash parser. This library decomposes the command into an abstract syntax tree, allowing us to inspect every command, argument, redirect, and pipeline token with absolute precision. The harness then compares this AST against a strict, deterministic security policy. It checks the base command against a strict whitelist of approved binary paths, such as git, npm, or pytest. It ensures that no forbidden commands, such as rm with recursive flags on root paths, or curl commands targeting raw IP addresses, exist anywhere in the syntax tree. If a forbidden token is detected in the AST, the command is blocked at the parser level. This check runs locally in microseconds, requires 0 token calls, and provides absolute mathematical certainty that cannot be bypassed by any prompt injection or semantic trickery. For code safety, we integrate static application security testing, or SAST, tools directly into our verification loops. Before any code patch generated by the agent is written to disk, the harness runs automated security scanners like SemGrep or Bandit on the modified AST. These scanners use concrete, syntax-based patterns and taint analysis to detect common security vulnerabilities, such as SQL injections, path traversals, insecure cryptographic configurations, or exposed API credentials. If a vulnerability is detected, the harness blocks the patch and feeds the structured SAST report back to the agent for remediation. Furthermore, we must implement advanced mathematical controls to prevent the doom loops we explored in Chapter 1. While simple backtracking and iteration limits provide basic protection, a production-grade harness must employ sophisticated, pattern-based loop detection. The harness tracks the trajectory of the agent's workspace changes over time by computing a running edit distance matrix of the files modified across iterations. If we map these edit distances as a sequence, a healthy debugging path looks like a descending curve, where the scale of modifications decreases as the agent zeroes in on the solution. A doom loop, however, exhibits a distinct oscillatory pattern. The agent edits a line, compiles, fails, edits the line back to its original state or to a minor syntactic variation, compiles, and fails again. The edit distance sequence bounces back and forth between a small set of states. When the harness detects this oscillatory pattern, it calculates the loop entropy of the trajectory. If the loop entropy falls below a critical threshold, indicating a highly repetitive, non-productive cycle, the harness activates a hard loop interrupt. It does not simply roll back the files. It dynamically re-architects the agent's execution path. The harness pauses the primary coordinator, serializes the failing state, and invokes an independent, high-level analyzer module. This analyzer is given the history of the loop, the failing test outputs, and a broader structural context of the codebase. It runs a deep reasoning trace to identify the systemic gap that the primary agent is missing, such as a missing database table or a circular dependency, and generates a structured redirect directive. The harness injects this directive into the coordinator's root context, breaks the loop, and forces the coordinator to adjust its planning DAG to address the root issue. This structural redirection ensures that our agents can break out of complex logic traps without wasting hours of execution time. To enforce compliance, regulatory alignment, and accountability, we must wrap these safety systems in a robust corporate governance framework. This is achieved by building cryptographically signed, immutable audit trails of all agent activities. The harness logs every transaction, system call, network interaction, tool invocation, and file system modification to a centralized, write-once-read-many database. Every log entry is packaged into a structured block and signed using a hardware-backed cryptographic key managed by the host infrastructure. These sign logs are streamed in real time to an independent security information and event management, or SIEM system. If an organization faces a compliance audit or a security investigation, they do not have to guess what their autonomous systems did. They possess an immutable, mathematically verifiable ledger that details the exact life cycle of every autonomous action. This deep governance architecture ensures that our agents remain completely transparent, audit compliant, and fully aligned with enterprise security policies. Let us now explore our final major component of advanced harness engineering: state persistence and memory systems. To build an agent that can work on long-running software projects over weeks or months, we must design systems that can maintain persistence across sessions and utilize a multi-tiered cognitive memory structure. In human cognition, memory is not a monolithic database. We operate using a complex, layered memory architecture consisting of working memory, short-term episodic memory, and long-term semantic memory. A production-grade agent harness must mimic this layered design. The first tier of this architecture is working memory. Working memory represents the immediate, high-fidelity physical state of the agent's current execution step. It consists of the sandbox file system, the active local Git branch, the open shell sessions, the running background processes, and the active local file caches. To make working memory truly persistent, the harness must support complete state serialization and snapshotting. If an agent is running a complex refactoring task that takes several hours, we must be able to pause the task, save the state, and resume it later, or transfer the execution to a different host machine in our infrastructure pool. We achieve this by utilizing container snapshotting technologies like CRIU, checkpoint/restore in user space. When a session is paused, the harness invokes CRIU to freeze the execution of all running processes inside the sandbox micro VM. It captures the exact state of the process memory registers, the open file descriptors, the local socket states, and the shell terminal history, serializing this process state into a set of image files. Simultaneously, the harness captures the file system diffs using the copy-on-write overlay layers we discussed earlier. It packages these process image files, file system diffs, and the serialized task DAG into a single unified state archive, storing it in a persistent cloud storage bucket. When the session is resumed, the harness provisions a fresh micro VM, restores the file system overlay, and uses CRIU to unfreeze the processes. The agent resumes execution instantly at the exact microsecond where it was paused, with all background processes, shell histories, and open file buffers perfectly intact. The second tier of our memory architecture is short-term episodic memory. Episodic memory tracks the chronological sequence of events, interactions, decisions, and outcomes within the current task lifecycle. It is the narrative history of the agent's journey. The harness manages episodic memory using a structured, indexed event store. Every tool invocation, compilation attempt, test failure, and self-correction decision is logged as a distinct event block. Rather than dumping this raw event store into the active context window, the harness builds an active retrieval index over the episodic memory. When the agent encounters a specific error, such as a database connection timeout, the harness uses a local search engine to query the episodic memory for previous occurrences of similar errors within the current task session. If a match is found, the harness retrieves the relevant event block, extracting how the error was resolved in the past. It injects this targeted episodic fragment into the active context. You encountered this exact database connection timeout in step 3 of your task. You resolved it by modifying the environment port mapping. Please apply the same corrective pattern. This targeted retrieval allows the agent to learn from its immediate past within the task session, preventing it from repeating the same debugging mistakes. The third tier of our architecture is long-term semantic memory. While episodic memory is localized to the current task, semantic memory spans across all tasks, repositories, and historical executions within the organization. It is the accumulated wisdom of the agent system over months of operation. Semantic memory is built by compiling and indexing successful execution trajectories. When an agent successfully completes a complex task, such as migrating a legacy API endpoint to a new service architecture, and its pull request is reviewed and merged by a human engineer, the harness processes the completed task history. It extracts the key semantic lessons from the trajectory. The original issue description, the high-level design plan, the specific modules edited, the core debugging patterns that were applied, and the final verified code diff. The harness packages this knowledge into a highly structured semantic memory artifact. This artifact is indexed and stored in an enterprise-wide vector database and a semantic knowledge graph. When a new task is initialized, perhaps for a completely different repository that shares a similar technology stack, the harness queries this long-term semantic memory. It retrieves the most semantically relevant historical task artifacts and injects them into the agent's initialization payload as high-value few-shot examples or architectural reference models. The agent learns from its organization-wide history. When we migrated similar endpoints in Project Y, we used this specific middleware wrapper to handle authorization headers. Please follow this established architectural pattern. This long-term memory system allows our agents to get progressively smarter, faster, and more aligned with our specific organizational coding practices over time, transforming a generic model into a highly institutionalized corporate engineering asset. As we bring this third chapter on advanced harness components to a close, let us review the incredibly powerful low-level systems we have designed. We have mapped out an isolated tool execution sandbox using Firecracker micro VMs, OverlayFS copy-on-write file systems, pseudo-terminal wrapping for interactive processes, and eBPF network containment. We have built a multi-agent actor model architecture capable of spawning focused subagents, orchestrating their communication over secure event buses, and enforcing strict, recursive token and process boundaries to prevent communication storms. We have designed a deep, OpenTelemetry compliant observability trace engine, combined with continuous, AST-driven reconciliation workers to manage system entropy and eliminate state drift. We have established an absolute security governance layer using fail-closed micro-VM lockdowns, deterministic AST-based shell command validation, automatic SAST checking, and mathematical loop entropy calculations to eliminate doom loops and enforce immutable audit compliance. And finally, we have engineered a multi-tiered memory and state persistence framework using CRIU checkpointing, episodic error retrieval indexes, and vector-based long-term semantic memories. By building these advanced components into our harness, we bridge the gap between AI and core systems engineering. We construct a secure, highly scalable, and deeply intelligent autonomous platform that is physically isolated from system hazards, logically structured to solve massive tasks, fully observable in real time, mathematically secure against system and security risks, and capable of growing and learning from its historical successes and failures. This is the zenith of modern harness engineering, building a digital runtime that is as robust, secure, and resilient as the enterprise software systems it is built to modify and maintain. Building a production-ready harness is an exercise in applied software systems engineering. Having mapped out the theoretical blueprints, control cycles, and advanced isolation mechanics of harness design, we must translate these concepts into a tangible codebase. In this fourth chapter, we will build a functional production harness from the ground up, utilizing modern open-source toolkits, standard protocols like the Model Context Protocol, and existing developer tools. We will then analyze real-world case studies across web development, back-end engineering, and legacy monorepositories, define concrete metrics to evaluate harness efficiency, and expose the most common architectural failure modes that derail enterprise agent deployments. To begin building a production-grade harness, we must establish its physical directory layout and class architecture. A clean, modular harness implementation is typically structured as an independent service package within a repository or as a standalone orchestrator service. In our implementation, we will design the core orchestration system in Python, leveraging its extensive static analysis ecosystem and standard systems programming libraries. Our harness directory is organized into 4 primary modules: the workspace controller, the execution sandbox, the tool registry, and the validation loop. At the entry point of our system, we instantiate a centralized runner class, which we will call the harness runner. This runner acts as the root coordinator, managing the execution state machine, loading configurations from the repository's agents.md file, and establishing the communication channel with our selected language model. Let us trace the physical code path that the harness runner executes when a new engineering task is initialized. The run method of our harness runner begins by instantiating the workspace controller. This controller is responsible for setting up the local file system environment. It uses the standard libraries Git module to clone the target repository branch to a designated workspace directory on our host machine, ensuring that all subsequent operations are performed on an isolated workspace copy rather than a live directory. Once the workspace is cloned, the workspace controller parses the agents.md file located at the repository root. It uses a YAML or Markdown parser to extract the structural metadata of the project, the exact locations of source directories, the command strings used to compile the code and execute the test runner, and any repository invariants. This structural metadata is loaded into a typed configuration object, which we call the project context. With the project context initialized, our runner invokes the execution sandbox. In a local development or testing environment, we can implement our sandbox using Docker's SDK, while in a high-scale production setting, we can swap this layer for a Firecracker micro VM pool. The sandbox class, which we name Docker Sandbox, exposes a clean programmatic API for file system operations and command execution. During initialization, the Docker Sandbox class builds a temporary container image. It reads a minimal Docker file configured to run a secure Linux distribution, mounting our host workspace directory into the container using a read-write overlayfs volume mount. This container is configured with strict security boundaries. We run the container process as a non-root user, disable all capability flags, and configure Iptable's rules to block all network egress except to explicit whitelist domains. Within the Docker Sandbox class, the execute command method is the workhorse of our execution layer. Instead of executing raw command strings, this method accepts an argument list to prevent shell injection. It invokes the Docker containers exec_create and exec_start APIs, capturing the standard output, standard error, and exit code streams using raw socket connections. This stout and stare stream is passed to a real-time monitor that terminates the process if its execution time exceeds a strict timeout limit, for example, 60 seconds, or if the output volume exceeds a safe threshold. To expose capabilities like file editing, structural code searching, and test execution to the agent, we implement a standardized tool orchestration layer using the Model Context Protocol, or MCP. The Model Context Protocol is an open standard designed to normalize how AI models interact with data sources and execution runtimes. By implementing MCP, we decouple our agent's cognitive engine from our local tools, allowing us to swap underlying models, whether we are using Claude Code, a custom model, or open-source local models without changing our tool execution logic. Our tool registry, named MCP Tool Registry, implements the core MCP server specification. It exposes a JSON RPC interface over standard I/O or WebSockets. Each tool in our harness is registered as an MCP tool definition, containing a precise JSON schema detailing its input parameters. Let us inspect the physical implementation of our file editing tool, which we register as the patch file tool. The JSON schema for this tool requires 3 parameters: the absolute file path, the original code block to replace, and the new replacement code block. When the model invokes this tool, the MCP server receives the JSON payload, validates it against the schema, and routes it to our workspace controller. Our workspace controller does not blindly write the new code block to the file. It first performs a strict safety and syntax check. It reads the target file from the file system, verifies that the original code block exists in the file, and runs a semantic diff to verify the target character coordinates. Before applying the patch, the controller invokes our static analysis module, AST Validator. This module uses the treesitter library to parse both the original file and the proposed modified version into abstract syntax trees. If the treesitter parser detects any syntax errors in the modified AST, such as missing semicolons, unmatched parentheses, or invalid structural blocks, the patch file tool instantly aborts. It returns a structured error payload to the model, containing the exact line and character coordinates of the syntax failure, completely protecting our file system from receiving broken, unparsable code. If the AST validation passes, the workspace controller applies the patch using a copy-on-write operation in our Docker Sandbox overlay layer. It then immediately triggers our verification loop, managed by the verification loop class. The verification loop reads the test execution command from our project context, for example, npm run test, and executes it inside our container sandbox. To optimize latency, our verification loop does not run the entire repository test suite on every minor file change. It uses an internal dependency analyzer to map the import graph of the project. When a file is modified, the dependency analyzer traverses the import tree to identify all modules that import the changed file. It then runs only the unit tests associated with those specific modules. The output of this test run is captured by our test runner interface. It parses the raw terminal output, extracting the total test count, the number of successful tests, and the exact error traces of any failing assertions. If the tests pass, the verification loop returns a successful validation state to the harness runner, allowing it to transition to the next step in its task graph. If the tests fail, the verification loop formats the test failure logs into a clean, contextual markdown block and feeds it back to the agent as an error observation, prompting it to self-correct. Having designed and implemented our first production-grade harness, let us now examine how this architecture performs in real-world environments. We will analyze 3 distinct case studies: a modern front-end web development workflow, a complex back-end API system, and a legacy monorepository containing millions of lines of code. Our first case study focuses on a modern front-end web application built using React, TypeScript, and a complex bundler pipeline. In front-end engineering, code correctness is not defined solely by whether the application compiles. It is defined by visual layout correctness, state synchronization, dynamic user interactions, and cross-browser compatibility. A traditional, non-harnessed agent attempting to edit a React component will frequently introduce silent visual regressions, break state hooks, or generate styles that overlap or break on different screen sizes. To build a successful web development harness, we must expand our verification loop to include visual and behavioral testing. Our front-end harness mounts a headless Chromium browser inside our container sandbox using a tool like Playwright or Puppeteer. When the agent proposes an edit to a React component, the harness intercepts the change, compiles the front-end bundle using Vite or Webpack, and starts a local web server inside the sandbox. The verification loop then launches the headless browser, navigates to the target page, and executes a series of automated behavioral scripts. These scripts simulate user interactions, such as clicking buttons, submitting forms, and expanding dropdowns, verifying that no runtime JavaScript exceptions are thrown in the browser console. To evaluate visual layout correctness, the harness uses pixel matching visual regression tools. Before the agent begins its task, the harness takes baseline screenshots of key application views using the headless browser. After the agent applies its modifications, the harness takes a matching set of screenshots and computes a visual pixel diff using a library like PixelMatch. If the visual diff exceeds a critical threshold, for example, if a CSS modification causes a sidebar to overlap with the main content area, the harness captures the visual diff image, highlights the overlapping layout elements, and returns a detailed visual error to the agent. Your layout changes caused a layout overlap in the sidebar container. Here are the coordinates of the visual collision. Please modify your CSS to use proper flexbox alignment. This visual feedback loop allows the agent to iterate on styling changes with the same level of precision as a human designer. Our second case study explores a back-end API system built with Node.js, Express, PostgreSQL, and Redis. Back-end development introduces a different set of challenges, particularly around state persistence, database migrations, asynchronous event processing, and external service dependencies. When an agent attempts to implement a new API endpoint or refactor a database schema, it cannot verify its changes without a running database and mock network services. Our backend harness solves this by orchestrating a local, containerized test environment using Docker Compose inside our sandboxed workspace. When the session starts, the harness spins up isolated instances of PostgreSQL and Redis alongside our application container, completely mimicking the production infrastructure. The tool registry for our backend agent includes custom SQL execution and migration verification tools. When the agent wants to modify a database schema, it does not write raw SQL migrations manually. Instead, it uses our schema migration tool. The harness captures the proposed migration script and executes it against the local sandboxed PostgreSQL database. If the migration fails due to a syntax error or a foreign key constraint violation, The harness captures the raw database error and presents it to the agent. If the migration succeeds, the harness automatically runs a schema verification script, extracting the new database schema structure and generating updated TypeScript interface definitions for the application's ORM model. Furthermore, our verification loop for back-end systems includes performance and integration testing. After the agent implements an API route, the harness executes a suite of integration tests using a library like Supertest. It verifies that the API endpoint returns the correct status codes, enforces proper JSON schemas on its responses, and handles authentication headers securely. To prevent performance regressions, the harness runs a lightweight load test on the modified endpoint using a tool like AutoCannon. It measures the endpoint's average latency, throughput, and memory consumption under a simulated load of 100 concurrent requests. If the endpoint's latency exceeds a safety threshold, for example, if a missing database index causes a query to take more than 200 milliseconds, the harness blocks the change. It returns a performance warning to the agent, prompting it to optimize its database query or implement query caching. Our third case study tackles the most demanding environment for any developer system: a legacy enterprise monorepository containing over 10 million lines of code written across multiple languages, including Java, Go, and Python. In a monorepository of this scale, running a full build or executing the entire test suite can take hours, and loading the entire file tree into a model's context window is physically impossible. To operate successfully in a large legacy codebase, our harness must employ highly advanced structural indexing and progressive context disclosure strategies. When the agent initializes inside the monorepository, our harness uses a fast structural indexer written in Rust to build an in-memory symbol graph of the entire project. This indexer parses every file, extracting the locations of class definitions, package namespaces, and module import paths. The tool registry for our legacy harness includes highly optimized navigation tools, such as the Find References and Go to Definition tools, which mimic the behavior of a professional language server protocol implementation. When the agent needs to understand how a specific class is used across the repository, it does not run slow text searches. It queries our symbol graph, which instantly returns the exact file paths and line ranges where the class is imported and instantiated. To manage the massive test suite of a monorepository, our verification loop uses advanced Bazel-style incremental build and test caching. The harness analyzes the target codebase dependency graph to identify the exact boundary of the affected subprojects. When the agent edits a Java class inside a specific service folder, the harness invokes only the local build target and executes only the unit tests associated with that isolated module. The build artifacts and test results are cached locally. If the local module tests pass, the harness runs a fast integration regression suite that targets only the boundary APIs of the neighboring modules, reducing the verification loop cycle time from hours to less than 45 seconds. This rapid feedback loop allows the agent to navigate and modify massive enterprise codebases with high confidence and minimal operational overhead. As we deploy these harnesses across diverse environments, we must establish a rigorous framework to measure their operational effectiveness. We cannot manage what we do not measure. To evaluate and optimize our harness designs, we define a set of key performance metrics, baseline benchmarks, and a centralized agentic trust score. Let us first define our primary system metrics. We divide our metrics into 3 categories: correctness metrics, resource efficiency metrics, and operational velocity metrics. Within correctness metrics, our primary indicator is the task success rate. This represents the percentage of tasks assigned to the agent that are completed successfully, passing all compilation, type checking, linting, and test suite verification gates on the first pull request submission. Alongside task success rate, we track the regression failure rate. This metric measures how often an agent's proposed changes pass the local verification loop, but introduce silent failures or break existing tests in other parts of the codebase that were not analyzed by the local verification loop. A high regression failure rate indicates that our test impact analysis or our dependency mapping is insufficient, signaling that we must expand the scope of our verification loop. Our resource efficiency metrics measure the economic viability of our agentic system. The primary efficiency metric is the token-to-resolution ratio. This ratio calculates the total number of input and output tokens consumed by the model to successfully resolve a single issue. A high token ratio indicates that the agent is struggling with context clutter, running into repetitive self-correction loops, or failing to converge on solutions quickly, signaling a need for better compaction strategies or tighter tool constraints. We also track the tool saturation index. This index measures the frequency and variety of tools invoked by the agent during a task. If an agent's tool saturation index is highly skewed toward a single tool, for example, if it is running text search dozens of times without finding the target files, it indicates that the search tool's API is poorly designed or that the agent lacks the structural context to navigate the repository efficiently. Our operational velocity metrics measure the speed of our system's feedback loops. The key velocity metric is the mean time to edit verification, or MTTEV. This calculates the average duration from the moment the agent proposes a file modification to the moment the harness returns the complete validation or execution feedback. To maintain a highly responsive agentic loop, we must optimize our sandboxes, compilers, and test runners to keep MTTEV under 30 seconds. If MTTEV drifts into minutes, the agent's overall task execution time scales exponentially, reducing its productivity compared to a human developer. To establish a baseline for these metrics, we run our harness against standardized industry benchmarks. The leading benchmark for evaluating software engineering agents is SWE Bench, which evaluates models on their ability to resolve real-world GitHub issues extracted from complex open-source Python repositories. As of 2026, the benchmark has evolved to include highly rigorous variations, such as SWE Bench Verified, which uses human-curated and verified test cases to eliminate flaky or ambiguous evaluations, and SWE Bench Multimodal, which tests an agent's ability to handle user interfaces, images, and visual layouts. While public benchmarks are valuable for general model comparison, they do not reflect the specific technical stacks, architectural patterns, and business logic of a private enterprise repository. To solve this, we must build a custom internal enterprise regression suite. Our engineering team compiles a baseline set of 50 historical bug tickets and feature requests from our own repositories. For each benchmark case, we record the original issue description, the target git commit, and the exact set of unit and integration tests that verify the resolution. We run our harness against this private benchmark suite after every major modification to our prompt templates, tool schemas, sandbox configurations, or compaction strategies. This allows us to empirically verify that our harness enhancements improve task success rates and reduce token consumption on our actual production code bases. To bridge the gap between automated testing and human trust, We combine these metrics and benchmarks into a single real-time metric, the Agentic Trust Score. This score is a formulaic index calculated by our harness state manager at the completion of every task. It determines whether the agent's pull request can be merged automatically into the development branch or if it must be routed to a senior human engineer for manual review. The Agentic Trust Score is calculated using 4 weighted parameters: test coverage delta, static analysis compliance, evaluation review score, and the execution trajectory complexity. The test coverage delta measures the change in code coverage inside the modified files. If the agent implements a feature but fails to write unit tests, causing the local coverage score to drop, this parameter penalizes the trust score. The static analysis compliance parameter evaluates whether the modified files have 0 linting warnings, 0 type checker errors, and pass all security vulnerability scans. The evaluation review score is the quantitative grade returned by our internal evaluator model, which assesses the semantic readability and architectural layout of the code. The execution trajectory complexity parameter measures the number of iterations and tool calls consumed by the agent to reach the solution. If the agent resolved the issue in 3 clean steps, it indicates high confidence. If it took 30 iterations, ran into multiple compilation failures, and barely passed the tests after extensive trial and error, the trajectory complexity penalty is high, reflecting a higher probability of latent bugs. If the calculated Agentic Trust Score exceeds our organization's high confidence threshold, for example 95%, the harness automatically marks the pull request as verified and merges the branch. If the score falls below the threshold, the harness flags the pull request for a manual review, appending the detailed breakdown of the trust score parameters directly to the PR comments to guide the human reviewer. This dynamic quality gate ensures that we maximize automation velocity while maintaining absolute control over the quality of our production code bases. As we implement these complex systems, we must remain highly vigilant against common architectural failure modes and anti-patterns. In harness engineering, subtle design errors can easily lead to catastrophic security vulnerabilities, exploding API bills, or unusable agent behavior. Let us dissect 5 of the most pervasive anti-patterns observed in enterprise agent deployments. Our first anti-pattern is the overprompted harness. This failure mode occurs when developers attempt to solve structural, mechanical issues by writing increasingly long, complex, and pleading system prompts instead of implementing hard system constraints and deterministic validations. For example, a developer might observe that their agent is occasionally editing files outside the target project folder, causing unexpected changes. In an overprompted system, the developer will modify the system prompt, adding lines like, "Please do not edit any files outside of the source directory. It is extremely important to only edit local files. Please be careful." This is a fragile, probabilistic fix. Under high cognitive loads or complex task instructions, the model will inevitably suffer from context drift and ignore these instructions. A professional harness engineer completely avoids this anti-pattern. Instead of prompting, they write a rigid computational constraint at the tool boundary. They update the write file tool implementation to resolve the target file path using absolute paths, verifying that the path starts with the sandboxed workspace root directory. If the path escapes the root directory, the tool immediately aborts and returns an error. By replacing soft prompts with hard, code-defined system validations, we guarantee absolute behavioral boundary compliance, reduce our token overhead, and free up the model's cognitive capacity for actual code reasoning. Our second anti-pattern is the brute force test runner. This failure mode occurs when the harness verification loop executes the entire repository test suite or runs a full application build on every single file edit or minor typo proposed by the agent. In a large code base, running the full test suite can take several minutes or even hours. When an agent is forced to wait for a slow build on every single iteration, the mean time to edit verification increases dramatically. The agent's cognitive momentum is shattered, and the total task execution time stretches into hours, rendering the system practically useless. To prevent the brute force anti-pattern, we must design highly optimized incremental verification loops. As explored in our case studies, we use test impact analysis, import graph mapping, and tool-assisted caching to isolate the exact subset of tests affected by a code modification. We must ensure that our baseline verification cycle completes in less than 30 seconds. If a test suite is inherently slow, we split it into a fast unit testing gate that runs on every edit and a slow integration testing gate that runs only after the agent has passed all local validations and is preparing to open its final pull request. Our third anti-pattern is context suffocation. This failure mode occurs when the harness design lacks active context management, continuously dumping raw, uncompressed files, entire terminal outputs, massive database schemas, and compounding historical error traces directly into the agent's active context window. As the conversation history grows, the model's attention is diluted. It becomes overwhelmed by the volume of noise, loses track of its primary objective, and begins hallucinating or repeating its previous mistakes. This leads directly to the doom loops where the agent makes the same incorrect edit over and over. We eliminate context suffocation by implementing the progressive disclosure and active semantic compaction strategies explored in Chapter 2. The harness must act as a strict information gateway, ensuring that the model only sees the absolute minimum data required for its current execution step. We must aggressively prune old logs, summarize previous execution epochs, and use structured symbol outlines instead of raw file dumps. By keeping our context windows lean, high density, and highly focused, we maintain peak cognitive alignment and maximize the reasoning accuracy of our models. Our fourth anti-pattern is the infinite sandbox escape. This is a severe security vulnerability that occurs when developers build a harness that executes the agent's tools directly on their local developer machines or within a poorly isolated container environment with host network access and raw file system permissions. In this setup, if the agent runs a command that executes a malicious script embedded in an open-source dependency, or if it is targeted by an indirect prompt injection exploit, the attacker gains immediate, unconstrained access to the host machine. They can read local SSH keys, steal environment variables, compromise internal network services, or delete critical local data. To secure our systems against the infinite sandbox escape, we must enforce a strict, fail-closed, secure by default isolation architecture. All tool executions, shell commands, and file operations must run inside completely isolated, micro-virtualized sandboxes, such as Firecracker micro-VMs or gvisor container environments. We must configure strict, read-only file system mounts for system directories, disable privileged execution flags, and implement eBPF-driven egress network filtering to block all unauthorized communication. A secure harness operates under the assumption that the agent's cognitive engine is untrusted, ensuring that its physical capabilities are strictly confined within an unbreakable digital vault. Our fifth and final anti-pattern is the shadow patching failure mode. This is a subtle but destructive operational anti-pattern where the agent makes direct, silent modifications to the running state of the application sandbox or file system without synchronizing those changes with the system's version control index or the harness's central state manager. Imagine an agent trying to debug a complex runtime issue. It executes a command that modifies a configuration file directly inside the container's active process directory, or it dynamically updates an environment variable inside its running terminal shell. The application compiles, the tests pass, and the agent reports success. However, because these changes were made silently outside of the tracked workspace directory, they are not committed to Git and are not included in the final pull request diff. When the code is pushed to production, the critical configuration change is missing, leading to an immediate production outage. To eliminate shadow patching, our harness must enforce absolute synchronization between the physical sandbox state and the tracking index. Every file modification tool must route its operations through our centralized workspace controller, which automatically stages the changes in Git and records the file system diffs. Furthermore, the harness should run a workspace reconciliation check at the end of every task. It compares the current state of the file system against the tracked Git index. If it detects any untracked modifications, modified files outside the workspace root, or modified environment variables that are not codified in the project's configuration files, the harness flags these changes. It forces the agent to codify these modifications into the proper configuration modules and commit them to the repository, ensuring that every single change required to run the application is fully captured, version controlled, and safely delivered to production. As we bring this fourth chapter on practical implementation to a close, let us review the incredibly robust systems we have constructed. We have built a functional, production-grade harness, establishing a modular directory layout, implementing a secure sandbox container runtime, and orchestrating highly secure, schema-validated tools using the Model Context Protocol and tree-sitter static analysis. We have explored real-world case studies, designing specialized visual regression testing for front-end web development, database migration and integration testing for back-end systems, and AST-driven indexing and incremental test caching to operate inside massive legacy monorepositories. We have defined a comprehensive measurement framework tracking critical correctness, resource efficiency, and velocity metrics, utilizing industry-standard benchmarks like SWE Bench, building private enterprise regression suites, and calculating a real-time agentic trust score to automate our quality gates. And finally, we have exposed and neutralized the most destructive failure modes of harness engineering, eliminating the overprompted harness, the brute force test runner, context suffocation, infinite sandbox escapes, and shadow patching. By mastering these practical implementations, we transition from theorists to system builders. We acquire the engineering capability to design, optimize, and secure the advanced runtimes that power modern autonomous development platforms, unlocking the true potential of AI-driven automation in our engineering teams. As software engineering transitions into a highly automated, agentic paradigm, the foundational structures of our discipline are being fundamentally rewritten. We are moving away from an era where human developers spend their days writing line-by-line syntax, managing low-level compile steps, and manually tracking dependency changes. Instead, we are entering a world where the primary unit of software construction is no longer the raw code itself, but the autonomous agentic system that generates, maintains, and verifies that code. This evolution demands a radical reassessment of how we define our roles as engineers, how we structure our development organizations, how we standardize our interfaces, and how we guarantee the absolute safety and reliability of our production systems. To understand this future, we must first examine the shifting role of the human developer in an agentic world. For decades, the measure of a software engineer was their command of syntax, their ability to memorize API surfaces, and their efficiency in transforming mental models into physical source files. In an environment powered by advanced execution harnesses, these tactical, syntactical operations are rapidly being offloaded to our autonomous agent fleets. This cognitive offloading does not render the human engineer obsolete. Rather, it elevates the developer from a tactical construction worker to a strategic system architect, policy designer, and high-context verifier. The human engineer becomes the ultimate supervisor of the automated workspace. Instead of writing code directly, the developer's primary responsibility shifts to defining the structural boundaries, declaring the system invariants, and specifying the precise verification criteria that the agent's harness will enforce. This shift represents a transition from imperative software development to declarative systems design. When facing a complex software requirement, the engineer does not begin by writing classes or functions. They begin by defining the destination state. They write the high-level system specifications, formalize the API contracts, and construct the comprehensive validation suites that define what correctness looks like for the target feature. Once these declarative guidelines are established inside documents like agents.md, the human engineer invokes the agentic harness. The harness then takes the wheel, orchestrating the specialized models, managing the isolated container sandboxes, running the compilers, and executing the test-driven feedback loops to generate the physical code implementation. The developer's interaction with this automated process is mediated through highly advanced, multidimensional human-machine interfaces. We are moving away from traditional, flat text editors toward highly interactive supervision dashboards. When reviewing an agent's contribution, the developer does not simply inspect a raw text diff in a pull request. The modern review interface provides a comprehensive visual decomposition of the agent's entire cognitive execution trace. The developer can inspect the planning DAG, see the alternative architectural paths the agent explored and discarded, review the compilation and test failures the agent encountered and resolved during its self-correction cycles, and analyze the performance load test metrics generated inside the sandbox. The human's role during this review is that of an auditor. They look for high-level semantic alignment, verify that the agent's implementation conforms to the organization's broader product vision, and inspect the code for subtle, qualitative design patterns that automatic linters and evaluators might have missed. If the developer identifies a flaw, they do not edit the files directly. They interact with the harness, injecting a high-level feedback instruction, directing the agent to revise its implementation. This collaborative feedback loop combines the speed, scale, and tireless execution of the autonomous harness with the high-context intuition, systemic reasoning, and ethical judgment of the human supervisor. As these individual developer workflows evolve, they trigger a profound, enterprise-wide organizational transformation. To survive and thrive in an agentic landscape, engineering organizations must restructure their teams, redefine their operational methodologies, and rebuild their technology platforms. We are witnessing the emergence of the harness-driven engineering team. In a traditional engineering organization, teams are structured around features, products, or service boundaries. Developers are assigned individual Jira tickets, and they work in parallel, merging their code into shared development branches through slow, manual pull request cycles. This human-centric workflow is characterized by high coordination overhead, long feedback loops, and significant communication friction. A harness-driven organization, however, restructures around platform engineering principles. Instead of assigning tickets to individual human developers, the organization deploys specialized fleets of autonomous agents to manage different domains of the codebase. The engineering department is divided into 3 primary tiers: platform harness engineers, domain policy designers, and strategic system architects. The platform harness engineers are the custodians of the execution runtime. They do not write business applications. Their sole focus is the design, security, and optimization of the enterprise-wide agent infrastructure. They build the secure, Firecracker-based virtualization pools, maintain the eBPF-driven network isolation layers, optimize the AST-driven codebase indexers, and develop the automated test impact analysis engines. Their goal is to provide a highly secure, lightning-fast, and deeply observable execution environment that any agent fleet can plug into. The domain policy designers are the developers who define the rules of engagement for specific business services. They possess deep domain expertise in areas like payment processing, identity management, or user interface design. Instead of writing features manually, they spend their time codifying their domain expertise into the project guidelines, custom linters, structural schemas, and evaluation rubrics of their target services. They ensure that any agent operating inside their service boundary conforms to strict regulatory requirements, security standards, and performance budgets. The strategic system architects operate at the highest level of abstraction. They look across the entire enterprise software ecosystem, designing the macro-level data models, defining the service communication interfaces, and directing the overall evolution of the digital product. They manage the high-level roadmap, ensuring that the work of the automated agent fleets aligns perfectly with the strategic goals of the business. This organizational restructure dramatically alters traditional software development methodologies. Agile and Scrum ceremonies are completely transformed. Sprint planning is no longer about estimating story points based on human developer hours. It is about designing the task graphs and defining the validation gates for our agentic systems. Daily stand-ups are replaced by automated telemetry reports that track the velocity, success rates, and token economics of the active agent fleets. Furthermore, the economics of software construction are completely redefined. In a traditional model, the cost of software development scales linearly with the size of the engineering headcount. In a harness-driven team, the cost of software execution becomes an asymmetric curve. While building the initial harness platform requires a significant upfront investment in platform engineering and infrastructure design, the marginal cost of executing subsequent software modifications drops by orders of magnitude. The organization can scale its development velocity exponentially by spinning up hundreds of concurrent agent sandboxes to implement features, fix bugs, and refactor legacy code bases simultaneously, while their human headcount remains lean, focused, and highly strategic. To support this massive cross-industry shift toward agentic automation, the software engineering community is rapidly developing open standards and shared frameworks. Just as the adoption of containerization required the standardization of OCI images and the Kubernetes API, the adoption of reliable software agents demands the standardization of how models interact with their execution environments. We are witnessing the birth of the open harness ecosystem. The most critical and rapidly adopting standard in this space is the Model Context Protocol, or MCP. Developed to solve the fragmentation of custom tool integrations, MCP establishes a universal, open client-server protocol that normalizes how language models communicate with local and remote data sources, tools, and execution environments. In an MCP-compliant architecture, the agent's core model acts as the client, while the harness tools and data sources run as independent MCP servers. The communication between the model and the tools is normalized using a standardized JSON RPC message envelope transmitted over standard I/O streams or server-sent events. Let us analyze the technical specifications of this protocol. The Model Context Protocol defines three primary resource types that an MCP server can expose to a model: resources, tools, and prompts. Resources are read-only data sources that provide context to the model. An MCP server can expose file system paths, Git commit histories, database query outputs, or API documentation as standardized resources. The model can dynamically query these resources using URI patterns, allowing it to navigate the codebase informational landscape without needing custom integration code. Tools represent the physical capabilities of the agent. Each tool is exposed as an executable function with a precise, schema-validated input signature. When the model wants to edit a file, run a build, or execute a test, it emits a standardized tool call request. The MCP server intercepts the request, validates the arguments against the declared schema, executes the physical operation inside the isolated sandbox, and returns the result in a normalized text or image format. Prompts are predefined, structured templates that guide the model through complex workflows. An MCP server can expose standardized prompt templates for common engineering tasks, such as generating code reviews, refactoring legacy classes, or diagnosing test failures. By adopting the Model Context Protocol, we achieve complete vendor-neutral decoupling in our harness designs. An engineering team can build a highly advanced, secure Firecracker execution sandbox and expose its capabilities as an MCP server. This server can then be navigated and utilized by any model, whether it is an open-source model running locally, an enterprise model accessed via API, or a specialized developer tool like Claude Code or Cursor. This standardization prevents vendor lock-in, fosters rapid community innovation, and allows organizations to continuously upgrade their models without needing to rebuild their underlying harness infrastructure. Alongside protocol standards, the community is developing mature, open-source harness frameworks that provide the building blocks of agentic execution. Early agent libraries, which focus primarily on conversational routing and simple chains, have evolved into highly robust, production-grade harness platforms. Modern open harness frameworks are designed as stateful, container-native runtimes. They provide built-in implementations of the advanced systems we explored in earlier chapters: directed acyclic graph orchestrators, type-safe schema validators, real-time log tracers, and multi-tier memory persistence adapters. These frameworks integrate deeply with container virtualization APIs, allowing developers to spin up isolated execution sandboxes with a single line of configuration. They provide pre-built, hardened toolsets for common software development environments, including fully configured compiler wrappers, test runner adapters, and static analysis integrations. By building upon these open-source foundations, organizations can construct their first enterprise-grade harness in days rather than months, accelerating the global transition toward reliable, automated software development. The rapid convergence of advanced model reasoning, micro-virtualization sandboxing, standardized communication protocols, and structured evaluation metrics is crystallizing into a completely new engineering discipline: reliable agentic software engineering. For years, the development of autonomous agents was treated as a branch of experimental machine learning or a hobbyist domain of prompt hacking. It was dominated by a mindset of trial and error, where success was defined by a model occasionally generating a working script under perfect conditions. This chaotic, probabilistic approach was fundamentally incompatible with the rigorous stability, security, and reliability requirements of enterprise production systems. Reliable agentic software engineering represents the maturation of this field. It is the application of rigorous, deterministic systems engineering principles to the orchestration of non-deterministic artificial intelligence. It is the transition from treating the model as an all-knowing oracle to treating it as a powerful, volatile computing core that must be governed, constrained, and verified at every step of its execution lifecycle. In this new discipline, we do not hope that the model will behave correctly. We build the physical systems that guarantee its correctness. We design the container sandboxes that isolate its failures, configure the eBPF filters that secure its network access, program the AST parsers that validate its syntax, write the dependency analyzers that optimize its test feedback, and compute the mathematical loop entropy metrics that prevent its cognitive decay. We treat the design of the harness with the same level of care, rigor, and architectural sophistication that we apply to our most critical production databases and microservices. We realize that the strength, reliability, and security of our automated systems depend entirely on the design of the harness that wraps around them. As we look to the horizon, the implications of this discipline are profound. The organizations that master the art of harness engineering will achieve a compounding, asymmetric advantage in development velocity, system reliability, and operational scalability. They will build software at a speed and scale that is completely unimaginable today, while maintaining absolute compliance, safety, and code quality standards. The software engineers who embrace this transition and cultivate deep expertise in harness architecture will position themselves at the vanguard of our industry. They will become the system builders, policy designers, and strategic directors of the automated enterprise, shaping the future of digital construction for decades to come. We have journeyed through the complete architectural landscape of harness engineering, uncovering the systemic design principles that elevate stochastic language models into highly reliable, autonomous software contributors. We began our exploration by establishing the core equation of our discipline: agent equals model plus harness, confronting the cognitive plateaus, attention drift, and statelessness of raw models that make a robust execution environment an absolute necessity. We then mapped out the blueprint of a production-grade harness, detailing the design of stateful directed acyclic graph steering loops, progressive context disclosure, and active semantic compaction to keep our models running at peak cognitive efficiency. We designed the feed-forward and feedback control systems, establishing type schemas, static AST guardrails, and firecracker-based micro-VM sandboxes to enforce absolute boundaries and protect our enterprise systems. We engineered advanced, self-correction feedback loops, utilizing targeted test impact verification, qualitative peer review evaluation, and multi-tier recovery patterns like backtracking and diagnostic subagent dispatching to allow our agents to autonomously overcome complex obstacles. We connected this architecture to the real-world software delivery lifecycle, designing seamless integrations with CI/CD pipelines and elegant human-in-the-loop approval workflows. We implemented these theoretical blueprints in a practical modular codebase utilizing the Model Context Protocol and analyzed their performance across real-world case studies in front-end, back-end, and massive legacy monorepositories. We defined a comprehensive measurement framework, tracking critical correctness, efficiency, and velocity metrics, establishing private enterprise regression suites, and calculating a real-time agentic trust score to automate our quality gates. We exposed and neutralized the most destructive failure modes of harness engineering, eliminating the overprompted harness, the brute force test runner, context suffocation, infinite sandbox escapes, and shadow patching. And finally, we envisioned the future of our industry, analyzing the transition of the human developer from code construction to strategic policy design, mapping the organizational restructuring required to build harness-driven teams, and exploring the standardization of open-source frameworks like the Model Context Protocol. By integrating these diverse systems, protocols, and mental models, we establish a permanent, secure, and highly scalable foundation for autonomous software delivery. We bridge the gap between artificial intelligence and computer systems programming, unlocking a new era of reliable agentic software engineering where our digital platforms are as resilient, safe, and robust as the code they generate.